Hello, one. This is Mr. Perry, and I'm testing something here. I'm making a video by using Blackboard Collaborate this time, and but I'm still going to upload this recording to Moodle, excuse me, to YouTube rather, and I'm going to make it present for the class to view later on. But anyway, I want to make a quick video and show you a few demonstrations as well, not just simply lecture, but do demonstrations of atmospheric pressure and Boyle's law. These two things I describe on the board behind me. So let me get out of the way of the board here and show you what I wrote. So real quick, everyone, you're going to read about atmospheric pressure. And atmospheric pressure comes from the weight of the air, let's say, interacting with each other. Like say you have different layers of air, for example, and what happens is as the gravity pulls this air down, that creates let's say a force on the other layers that's beneath that particular layer of air, and that leads to the creation of atmospheric pressure. So what happens is you have the weight of, or you have all the collisions of the air molecules with each other, and saying counteracting the way of gravity, that gives rise to pressure. So as you look at the layers of air above the ground on our planet, what happens is as you go further down, as you go down from the top layer to to the layers closer to the ground, what happens is atmospheric pressure will increase. And the reason why the atmospheric pressure increases, everyone, because if you think of the layers, and if I was numbering, let's say this is like one, two, three. Actually, let's make this one here. Let's say one, two, three, four, and then like underneath you have five. And what happens is, everyone, is that this top layer, number one, this is like say again, it's like the top layer of the atmosphere. What happens is this layer, this atmospheric gas fades out into space. But for the most part, the atmospheric pressure here in layer one will be the lowest. So it's the lowest pressure. And the reason why is because you don't have anything above it to really push it down. But if we get to like saying layer two, this one's a little higher. So this would be the next lowest. Okay. And what happens is, everyone, is that you see the reason why the pressure here is greater than number one is because you got the weight of all the air here it said layer one on top of layer two. Okay. One example that people often use is pillows. If I will take let's say a set of pillows, let's say I take 5 pillows and stack them up. What happens is that the pillow on top is still kind of fluffed up. The pillow, like I said, the second pillow from the top, it's still kind of fluffed up, but not as fluffed up as one. Now we get to three. What happens is between the pillows and the air, what happens is that you got this layer and this layer on top of this layer. So this layer is going to be more compacted and therefore higher pressure. Whereas four, the pressure gets even higher because now you got one, two, three, and three, the weight of all of these on top of that layer. Same thing with the pillows. By the time you get to say pillow four, that pillow is squished a lot more because you got the weight of the other 3 pillows on top. Now we get to the last pillow and therefore the last layer of air, let's say five. Now you got the weight of all these on top of it, and like that. So always those motion sensor lights are just in a trip. If you don't move, they go off. But what happens is, everyone's that now in layer five, I got the weight of all these four on top of it, and therefore it gets squished a lot. If you're talking about pillows. Now going back to atmospheric pressure also synonymous with what's happening with the pillows is that now I got the weight of all this air on top of the layer five. Okay, so layer five, this is the highest. This is the highest when it comes to pressure. Okay, because you got a weight of all of these on top of layer five. Just like with the pillows, if you stack up some pillows, the one at saying five would be the most squished, or therefore the highest most pressurized pillow. So another thing about this, everyone, related to that, make sure you note to yourselves, pressure increases with depth. Okay? So, in other words, the greater the depth is, the greater you go down depth in a fluid. This works for liquids as well as it does, let's say, gases. So, what happens is, as you go, let's say, increase it in depth, what happens is that say the layer or the level that's at the lowest depth, that's going to be the most pressurized depth. It's like water. For example, if you submerge yourself in water, as you go to greater depths, they're saying the pressure increases because now you got layers of more water on top of you as you go further down. Okay, so and to give you another demonstration of that, and lead to, let's say again, the related topic, Boyle's law. Let's take a look at this. So I'm gonna share this screen with you, and when you look at these, this again from the Colorado website. All right. So I'm going to gas properties here. Play this. Okay. So I'm going to first deal with ideal gas. Matter of fact, I'm just going to simply deal with ideal gas. So let's say my atmosphere saying pressure. As I put gas inside this chamber, look how the pressure meter went up. Now, everybody, we measure pressure in several different units. One unit is one atmosphere or atmospheres, and one atmosphere would be the atmosphere of Earth. That's equal to so many, like saying bar, which is equal to so many kilopascals. Okay, the base unit in SI is kilopascals, but we also prefer to use, like saying units like a bar is in barometer, which is the device we use to measure air pressure or atmospheric pressure, as well as fluid pressures in general. We measure those in units of bar or atmospheres. Okay, so pounds per square inch is another same related unit to because that's of course pounds per square inch. That goes back to the definition that force divided by area gives you or defines pressure. So everybody look at how let's say again have these air molecules bounce around inside this chamber. And I say that the atmospheric pressure fluctuates because their molecules are constantly moving around. And so therefore as they collide with each other, they're going to change the pressure. And there's gravity acting on these particles as well. So what I could do is, and I believe, I'll go here. That's the particle counter there. Okay. And okay, this is the ideal gas. So I don't have a function here. I don't have a function here, although in the old version of this simulation, I did have that function where I could change the gravity. If I were to change the gravity, everyone, what you'll notice is that if I increase the gravity, the pressure will actually go up. And the reason why the pressure will go up is because by increasing the gravity, I increase the weight of the air, and therefore, let's say again, when they interact with each other, you got a great amount of weight to deal with, and that would therefore increase the pressure. I can also increase the pressure by doing this. Well, actually, this is the better thing to note. Increase the air pressure by basically having essentially more air molecules in that unit of volume. As I was saying in my earlier video, what happens is that gases fill up a container, no matter what the volume of the container is. So if I'll do this, if I were to change the volume of this container, let me use this my arrow here and pull it back. Now look at the pressure, by the way, and this is the Boyle's law. Look what happens with the pressure when I increase this chamber. Notice how the air pressure is going down. I increase the volume, and the air pressure goes down. And so what happens is, everyone, is that, and this leads directly to Boyle's law, and let me go ahead and stop sharing this and go back to the board here. Boyle's law says this: pressure and volume are related to each other. They're inversely proportional to each other. So if you multiply pressure and volume with each other, you'll get a constant value. Okay? And so that's what Boyle's law starts. So this is what Boyle's law is saying. If I were to increase the pressure, in order for the product of pressure times volume to stay constant, the volume must go down if I increase the pressure. Whereas I decrease the pressure, the volume must go up in order for the constant of the product of pressure times volume to stay the same. Okay? So in other words, again, let me say it this way. Pressure increases, volume decreases. And volume, or rather pressure decreases, volume increases. Okay? So one way of looking at this, let's say I take this for example. Let's say I take two different scenarios. Scenario 1 and scenario 2. P1 times V1 is equal to P2 times V2. So let's say P1 is 100 kilopascals and V1 is 300 cubic meters. Okay? So P2 is 10. So what is V2? Okay? So what I do is apply my equation. 100 times 300 that's going to be equal to 10 times what V2 is. And solve for V2, I do some just simple division. So just like you saw me while saying doing that simulation, okay? What I did was I increased the volume, which decreased the pressure. So what you expect to happen here is this. I got 100 times 300, let's divide by 10. 100 divided by 10 is going to give me, of course, 10. So 10 times 300 gives me 2,000. So again, by decreasing the pressure, I increase the volume. And that's what you just saw me do in the simulation. Let me go back to the simulation now. So let's share that with you again. So everybody look at this. What I'm gonna do this time is I'm gonna increase, or rather decrease the volume. Notice how the pressure went up. I keep decreasing the volume. Pressure keeps going up. They say the presentation I posted on Moodle did it this way. If you double, say again the pressure, you cut the volume in half. Okay, so I keep decreasing the volume. That increases the pressure. And everybody, what happens is with this simulation, if I decrease the volume enough, the pressure inside will increase to the point that it will actually blow the chamber open. But instead of doing that, let me do this. I'm just open the chamber. I'm letting the air out. And look what happens as I let the air out. No surprise, I got fewer air molecules in my container, and therefore, as the particles get fewer and fewer, I decrease the pressure. Now let me actually increase the volume here too at the same time. So it's definitely going down now. Okay, but everybody, this is why I want everybody to understand, and this is why I want to reiterate from my earlier video, is that no matter how much gas I got, what little gas I have is going to fill up that chamber. Okay, if you want to have no gas in the chamber whatsoever, all the air molecules got to get out. But good luck with that happening, because what's going to happen is that thanks to diffusion, is that if you got air on the outside as well as air on the inside, there's always going to be air in the chamber. Because of the diffusion, what's going to happen is once the air inside the chamber gets too low, the air on the outside chamber is going to start forcing air back in. Okay, what's going to travel? Air is going to travel back in, because now you have a lower pressure inside than you do outside, and that leads to again what I said, diffusion. All right, so you didn't really consider that in the simulation, but you also you will see that in reality. Another thing related to pressure and volume, everyone, is temperature. Let me close the chamber again. Increase the heat. Turn the heat control on. I keep that pushed up. And look what happens. you have temperature increase, and therefore you have an increase in pressure. Later on, when saying in later chapters actually coming up right after phases of matter, it's right after we finish those chapters, we're going to start discussing heat and temperature. And what we're going to see in those chapters is the relationship between pressure, volume, and temperature. Okay, and just for my own curiosity, I'm gonna put up this collisions counter. Hit play. Look how many collisions we're getting here. Okay, so in that sample period of saying 10, picoseconds, I had 731 collisions. Now everybody, I'm gonna increase the heat, and what happens when I increase the heat? Notice how again, because the heat increases the pressure. What happens is I create the pressure so much that it blew the lid off the container. So I'm returning the lid. Obviously, the pressure is gone down a lot, but because I increased so much, so many particles went down. And if I'll do another, let's say counter here. Okay. So again, this is like I said, the reason why I'm also showing this simulation is because this simulation later on with your lab coming up this week, this week or next week. So stop sharing that. Let me show you another thing you can make at home. Everybody, this thing here is a vortex cannon. And one way of making this is one way of making a vortex cannon. Just take a box, tape it up, and on one side, cut a hole. Okay? And what happens is, just to show you again, that air always fills up a container, or gases always fill up a container. What I'm gonna do is that I'm gonna take this box, put a piece of paper over the hole in the box, and then I'm gonna slap the box. I don't have to slap it. I can simply push it. And what happens, everybody, when I push on the box, I'm compressing it. So as I compress the box, I'm gonna make the volume smaller. If I'm making the volume smaller, according to Boyle's law, what's gonna happen to the pressure? Increase. So what happens is when I increase that net pressure, it's gonna create a flow of air out of the box. And next thing you know, paper comes off. So now if I just simply pushing, really not that dramatic or dynamic for that matter. So, but if I was to slap the box, see how fast that paper came off? You know what I'm saying? By slapping the box, that rapid compression, that create a rapid flow of air, and therefore, let's say the box, or the air rather, rushing out of the box blew that piece of paper right up in the air very quickly. Similarly, a similar thing, I have this air tank here, and this is actually what this thing does is it's designed to do take air out and use a motor rather, create a suction and blow air out of this hole. So it's something you use to blow up balloons basically. So I press down this thing to make it work. This time, instead of rushing air, when I had rushed air out of this container, the air that rushed out of this container, or rushed through this container, I should say, rushed into this container, the balloon. So why does the balloon inflate, everyone? The reason why a balloon inflates is because if you rush air into the balloon, that greatly increases the pressure inside. And what happens is the balloon's going to expand until you have a balance of pressure inside and outside the balloon. So once the pressure on the inside and outside of the balloon are equal or balanced, you have no change in the volume of the balloon. If I let the air out of the balloon, pressure now on the inside is decreasing, and it continues to decrease until the pressure inside and outside are equal to each other. So everybody, while the balloon stays like this, I closed off the balloon, and so now that the pressure on the inside as well as the pressure on the outside of the balloon are the same, and therefore it maintains a certain volume as a result. Okay. So again, if I want to make the balloon expand, change its volume, I got to change the pressure on the inside. Okay? And so again, that's how Boyle's law relates to like things like at least balloons, how they expand. Right. One last thing. Say I mentioned Bernoulli's principle in my earlier video. I can demonstrate Bernoulli's principle, and there's several ways of demonstrating Bernoulli's principle. But one common way of demonstrating Bernoulli's principle, everyone, let me lower the camera down so you can see this. Let's see, actually, I don't think I can. The stand will lower it more down so you can see it. See it. So I'm just gonna have to hold the computer. But everybody, what happens is, again, if I were to press down on this blower, and of course, air is gonna be saying pushed on the air is gonna start pushing on the ball. The ball will go up in the air, but also the ball is suspended in the air. Okay, if I kept the air going, the ball will still be suspended way up in the air off camera. And what happens, everyone, is that by rushing the air around the ball, what happens is, everyone, I change the pressure around the ball, the pressures around the ball. You have a top pressure, for example, and you have a bottom pressure to the ball. Well, of course, those are equal to each other. Ball doesn't move; it just sits there. Okay, but if I was to create, say, a rapid flow of air, that would change the pressure on the tops and the bottom. And by having that pressure differential, just like I did with the balloon, but I create a pressure differential. In this situation, I suspend the ball in air. Everybody, look what happens when the ball comes down. See how it's rotating around? So, well, off the table now. But everybody, what happens is that fast moving air tends to lead to, for enclosed fluids, fast moving air tends to lead to a lower, saying like pressure. Like say we have an airflow over, like say, over a surface. The airflow, saying you have an airflow also under the surface too. I should add. And what happens is if the airflow over the top is faster than the airflow on the bottom, you have a lower pressure on the top than you do on the bottom. And that is, in a nutshell, Bernoulli's principle. And that is basically what airplane wings are designed to do. Airplane wings are designed such that you have a greater, or more, I should say, a more rapid airflow over the top of the wing versus the bottom of the wing. And what happens is that lower pressure on the bottom of the wing versus the top of the wing creates a lift. Because now you have an imbalance between the two of them. You have a pressure differential. And so therefore, due to that pressure differential, that allows lift to be created, and that allows also for the plane to basically fly. Okay? The other part, of course, planes flying is that the process of the airflow creates drag. So what happens is that planes have engines to create thrust, because without that thrust, the plane will not overcome the drag, and the drag would cause the lift to go away, because the drag would cause the speed to go down. So how the planes create a greater airflow over the top of the wing is by having some actual speed, having it, it actually has to go or be propelled forward in some kind of way. Okay, so the engines do two things: create thrust, and as well as create that saying that rapid airflow that you need to go over the wing to create lift. So the two go hand in hand. Okay, wings are also a certain size such that the more air you displace, creates more lift. In other words, the more more the plane pushes down on the surrounding air, the more the surrounding air pushes up on the plane. Okay, and again, that goes back to Newton's third law. But that also illustrates Archimedes' principle. And Archimedes' principle can be argued to be the true reason or the true explanation why planes create lift, or how planes create lift. I should say how planes create lift. So everyone, this is Mr. Perry, and again, signing off for right now. And if anybody has any questions about this video or anything else you saw in the previous video I posted for this week, let me know.